Imagine for a moment, drifting far beyond the reach of any star, any planet, any nebula, into the deepest, darkest stretches of intergalactic space. Here, light from distant galaxies takes millions of years to arrive, and matter is spread so thinly that you might travel for light years without encountering a single atom. We often picture this ultimate vacuum as a perfect void, utterly empty, silent and still, a pristine canvas of absolute nothingness. It is the very definition of absence, a place where all activity ceases, where the very fabric of existence seems to stretch into an infinite, featureless expanse. This perception of an empty cosmos, silent and unchanging, has been a cornerstone of human thought for millennia. Yet, what if this profound stillness, this tranquil emptiness, is merely a grand illusion? What if, beneath the calm surface of the void, there lies an unseen, ceaseless commotion, a fundamental hum of activity that permeates every single point in the universe, even where there appears to be nothing at all? Could the truest vacuum, the most profound absence of matter and energy, actually be a vibrant, bustling arena, teeming with fleeting, ephemeral phenomena? This notion profoundly challenges our intuitive understanding of reality, pushing the boundaries of what we conceive as empty. Does this quiet roar of nothingness truly exist? Modern physics, specifically the quantum realm, reveals a startling truth that reshapes this very concept. At the most fundamental scales, the universe behaves in ways that defy our everyday experiences. Here, particles are not tiny, solid balls, but rather fuzzy probability waves, and energy itself is not a smooth, continuous flow, but rather comes in discrete packets. In this strange domain, the idea of an absolute void, a space utterly devoid of anything, begins to unravel. Instead, the vacuum is unveiled as a dynamic, energetic medium, a place where energy itself can fluctuate in bewildering ways, momentarily conjuring particles into existence before they vanish just as swiftly. It is a cosmic dance happening at scales so minuscule and speeds so unfathomably fast that it remains entirely imperceptible to our senses. Yet it forms the very bedrock of our reality. These fleeting entities are known as virtual particles. They are not quite the stable, observable particles that make up atoms or light, but rather ephemeral ghosts, temporary loans from the universe's energy budget. Think of them like bubbles forming and popping in boiling water. But instead of water, it is the very fabric of space-time itself that is boiling with these phantom presences. They flicker into being as particle-antiparticle pairs. For instance, an electron and its antimatter counterpart, a positron, exist for an unimaginably brief moment and then annihilate each other, returning the borrowed energy to the vacuum. This continuous, spontaneous generation and annihilation is not a rare event, but an incessant, universal phenomenon occurring everywhere, all the time. It is a fundamental property of the universe, a restless, bubbling sea of potential that never truly settles into absolute emptiness. This ceaseless activity is rooted in what are called quantum fluctuations. Even in the deepest vacuum, where all matter and radiation have been removed, the energy levels are not static. They are inherently uncertain, constantly fluctuating or jittering. This fundamental jitter allows for temporary violations of energy conservation, meaning, for an incredibly short time, a tiny amount of energy can seemingly appear out of nowhere. This borrowed energy is then immediately repaid when the virtual particles, which were created from that energy, vanish back into the vacuum. It is a cosmic accounting trick where the books are always balanced in the long run, but in the short term, there is a flurry of borrowing and repaying, creating a dynamic, ever-changing environment, even in what we perceive as ultimate stillness. This constant flux of energy and matter, appearing and disappearing, is often poetically referred to as quantum foam, a vivid metaphor for the bubbling, seething nature of the vacuum at its most fundamental level. So if every speck of empty space is actually a stage for this rapid-fire creation and destruction of virtual particles, can we truly speak of emptiness anymore? Our conventional understanding of a vacuum as a passive container for the universe is fundamentally challenged. Instead, we must conceive of it as an active participant, a vibrant medium with intrinsic properties and dynamic behavior. It is not just the absence of things, but a teeming potentiality, a substrate from which everything else emerges and into which everything eventually returns. This redefinition of emptiness is not merely an academic exercise. It has profound implications for understanding the universe on scales both microscopic and macroscopic. It suggests that nothing is not inert, but rather a profound wellspring of activity, a dynamic entity that contributes to the very fabric and evolution of the cosmos. Consider the implications. If the vacuum itself is not truly empty, but instead a churning sea of potential, how does that influence the space around us, the forces we experience, and even the expansion of the universe? It suggests that the seemingly tranquil void is, in fact, incredibly energetic. The sheer density of these quantum fluctuations, occurring at every point in space-time, implies an astonishing amount of inherent energy. For instance, theoretical calculations based on the known principles of quantum mechanics suggest that a single cubic centimeter of empty space, about the size of a sugar cube, could possess enough vacuum energy to boil all the oceans on Earth. This is an almost incomprehensible amount of energy, hidden in plain sight, challenging our perceptions of what is truly substantial. How can such immense theoretical energy remain mostly hidden from our everyday experience? This inherent energy of the vacuum, often called vacuum energy, is not a fringe idea. It is a direct consequence of combining quantum mechanics with the concept of fields that permeate space. Every fundamental field in physics, the electromagnetic field, the electron field, the quark field, has a minimum energy state, even when it appears empty of particles. This minimum energy is the vacuum energy of that field. When you sum up the contributions from all these fundamental fields across the entire universe, the theoretical vacuum energy density becomes truly staggering. It's a fundamental property that pervades everything, everywhere, all the time. It's a background hum, a subtle but omnipresent force, shaping the very nature of reality in ways we are only beginning to comprehend. This constant, unseen activity is not just a theoretical construct. It hints at a deeper, more profound truth about the universe. It suggests that existence itself is an ongoing process, a continuous creation and dissolution, even at its most fundamental level. The universe is never truly static, never truly devoid of motion or change, even in its most barren reaches. This quantum foam, this quiet roar of nothingness, might not just be an interesting footnote in physics, but a defining feature of our universe, an underlying engine-driving phenomena on scales we can barely imagine. It sets the stage for a universe far more active and mysterious than the simple, static void we once envisioned. As we delve deeper, we will uncover how this seemingly impossible activity manifests in measurable ways, and how it might even be shaping the destiny of the entire cosmos. What tangible evidence could possibly confirm such a bizarre and counterintuitive idea? As we gently drift through the cosmic quietude, perhaps contemplating the vast, seemingly empty stretches between stars, a profound question arises. If space truly is a void, how can it possess such a vibrant, hidden life? The previous journey revealed that even the deepest vacuum is not truly empty, but rather a seething cauldron of activity. Now, we delve deeper into the fundamental principles that govern this invisible ballet, exploring the very rules that allow nothing to become something, even for the briefest flicker of existence. What fundamental laws of nature permit particles to spontaneously emerge from the void, only to vanish again in an instant? The answer lies in the enigmatic realm of quantum mechanics, a set of rules so counterintuitive that they often defy our everyday experience, yet they accurately describe the universe at its most microscopic scales. Our familiar world operates under predictable rules. A ball thrown into the air follows a clear trajectory, and a car driving down a road maintains a consistent speed, unless acted upon by an external force. Energy, we are taught, is always conserved. It cannot be created or destroyed, only transformed. These classical laws, however, begin to fray and unravel when we zoom in, past the atoms, past the nuclei, into the subatomic substratum of reality. Here, at scales unimaginably small, the universe begins to behave in profoundly strange ways that allow for the ephemeral appearance of particles from what appears to be absolute nothingness. Central to this quantum magic is a concept known as the Heisenberg uncertainty principle. This isn't just about our ability to measure things. It's a fundamental statement about the universe itself. Imagine trying to precisely locate a tiny, buzzing bee and simultaneously know its exact speed and direction. In our everyday world, with enough care, we could measure both. But in the quantum realm, for certain pairs of properties, the universe itself imposes a limit. The more precisely you know one property, the less precisely you can simultaneously know its paired property. It's not a limitation of our instruments, but an intrinsic property of reality. For our exploration of vacuum energy, the crucial pairing within the Heisenberg uncertainty principle is that between energy and time. The principle states that you cannot simultaneously know the exact energy of a system and the exact moment in time that energy is present with absolute precision. Mathematically, this is often expressed as an inequality. The uncertainty in energy multiplied by the uncertainty in time must be greater than or equal to a tiny fundamental value related to Planck's constant. What this implies is truly astonishing. For a very short period of time, there can be a temporary, fundamental uncertainty about the exact amount of energy present in a given region of space. This isn't a true, permanent violation of the law of conservation of energy, but rather a fleeting allowance, a cosmic IOU. Think of it like this. The universe has an extremely strict cosmic bank. You are allowed to momentarily borrow energy from this bank, but there are two ironclad rules. First, you must repay the loan incredibly quickly. The more energy you borrow, the faster you must return it. Second, when you borrow energy, it doesn't just sit there. It manifests itself. This borrowed energy, according to Albert Einstein's famous equation E=mc2, can be converted into mass. And so, out of the empty vacuum, pairs of particles and their corresponding antiparticles can spontaneously materialize. Consider an electron, a fundamental particle carrying a negative electrical charge, and its antimatter counterpart, a positron. A positron has the exact same mass as an electron, but carries a positive electrical charge. In the quantum vacuum, if enough energy is momentarily borrowed, it can manifest as an electron-positron pair. They pop into existence together, like two sides of a coin, born from the very fabric of space-time itself. But the rules of the cosmic bank are absolute. The borrowed energy must be repaid. So almost immediately after their creation, these particle-antiparticle twins encounter each other. When an electron and a positron meet, they mutually annihilate, converting their combined mass back into energy, which is then returned to the vacuum. This repayment happens so quickly that, on average, over any measurable period, the total energy of the universe remains perfectly conserved. How incredibly quickly does this all happen? For an electron-positron pair, their entire existence, from birth to annihilation, might span a mere 10-21 seconds. To put that into perspective, imagine a single blink of your eye, which takes about 1/10 of a second. The lifetime of these virtual particles is a trillion times shorter than that blink. They are truly phantom presences, fleeting ghosts in the machine of reality, existing for timescales so brief that our minds struggle to grasp them. And what about the scale of their appearance? These aren't macroscopic objects. They are subatomic, arising in regions of space far smaller than the nucleus of an atom. If we were to imagine an atom scaled up to the size of Earth, its nucleus would be roughly the size of a football stadium. The quantum fluctuations giving rise to virtual particles would then be occurring in regions smaller than a speck of dust on that stadium field. These are truly microscopic events, happening in the most infinitesimal corners of what we perceive as emptiness. This constant, furious activity of virtual particles appearing and disappearing, borrowing and repaying energy, is what physicists refer to as the quantum foam. It's not a static, serene void, but an effervescent, bubbling sea of potential. Picture the surface of a boiling pot, but instead of water molecules, it's tiny packets of energy and matter constantly churning, rising and vanishing. This foam isn't just in some distant exotic corner of the universe. It permeates all of space, including the empty space right around you, within you, and between the stars. It is the ceaseless, energetic jitter that underpins the very fabric of reality, a fundamental quantum uncertainty that ensures true emptiness can never exist. So if this quantum foam is everywhere, constantly generating and annihilating particles, does it have any tangible effects on our macroscopic world? Or is it merely a theoretical curiosity confined to the realm of the impossibly small and vast? This question leads us to some of the most profound and unexpected discoveries in physics, suggesting that this invisible dance might not be so invisible after all. Could these fleeting quantum events, happening on scales we can barely comprehend, somehow leave a measurable imprint on our world? The answer, as we will soon discover, is a resounding yes, and it leads us to one of the most elegant and surprising demonstrations of vacuum energy, the Casimir effect. In the quiet depths of space where classical physics once envisioned a perfect, serene void, we've begun to uncover a startling, ceaseless activity. The quantum foam, as we've learned, ensures that even the most profound emptiness is, in fact, a bustling arena where virtual particles flicker into existence and vanish in an instant, borrowing and repaying energy from the universe. But could something so ephemeral, so fleeting, so utterly invisible, truly leave a tangible mark on our physical world? Could these phantom particles, which exist for mere fractions of a second, exert a real measurable force? The answer, surprisingly, is yes. The quantum vacuum, far from being inert, possesses a subtle yet profound power. one that has been experimentally proven to exert a tiny, persistent push or pull. This remarkable phenomenon is known as the Casimir effect, and it offers one of the most compelling pieces of evidence that the vacuum is anything but empty. Imagine, if you will, two perfectly smooth, uncharged metal plates. Now, bring them incredibly close together, perhaps just a few hundred nanometers apart. That's a distance far smaller than the width of a human hair. Place this delicate arrangement into a perfect vacuum, removing all air and any other stray particles. What would you expect to happen? Classically, if the plates carry no electric charge and there's no air pressure or gravity to consider, they should simply float there, utterly oblivious to one another. Yet, under these precise conditions, a faint, undeniable attractive force emerges, gently pulling the plates closer. This is the essence of the Casimir effect, a direct whisper from the quantum realm. How can this be? The explanation lies in the ceaseless dance of virtual particles we discussed earlier. Think of the vacuum not as empty space, but as a vast, energetic ocean, constantly churning with ripples of energy that manifest as these fleeting particle-antiparticle pairs. All around us, and indeed, throughout the entire universe, this quantum foam is vibrating at every conceivable wavelength and frequency. It's like an orchestra playing every possible note all at once. Now consider what happens when we introduce those two metal plates. The space outside. The plates remains an open, boundless ocean where virtual particles of all wavelengths can freely appear and disappear. They contribute to the total vacuum energy in that region without restriction. But the space between the plates is different. It's a confined cavity, a tiny quantum bottleneck. Just as a guitar string can only vibrate at specific resonant frequencies, or a pipe organ can only produce certain sound waves determined by its length, the virtual particles between the plates are restricted. Only those virtual particles whose wavelengths precisely fit into the narrow gap between the plates are allowed to exist for their fleeting moments. Longer wavelengths, which would extend beyond the plates, are effectively suppressed. It's as if a filter has been applied, allowing only a subset of the quantum orchestra to play within that tiny space. This restriction creates an imbalance. There are fewer modes or fewer types of virtual particles contributing to the vacuum energy between the plates compared to the unrestricted vacuum outside the plates. The pressure from the more diverse and numerous virtual particles outside the plates is effectively greater than the pressure from the limited types of virtual particles inside. This differential in vacuum energy density then manifests as a net force, pushing the plates inward towards each other. It's not a mysterious attraction emanating from the plates themselves, but rather a push from the quantum vacuum surrounding them. Is it not truly remarkable that nothing can exert such a tangible influence? The theoretical prediction of this effect dates back to 1948, conceived by the Dutch physicist Hendrik Casimir. At the time, Casimir was working at Philips Research Laboratories, exploring the fundamental forces between neutral atoms and molecules, known as van der Waals forces. These forces are crucial for understanding everything from the adhesion of geckos to surfaces to the stability of colloids. In his investigations, Casimir realized that the zero-point energy of the electromagnetic field, which is essentially the lowest possible energy state of the vacuum, even at absolute zero temperature, should contribute to these interactions. He meticulously calculated that two perfectly conducting parallel plates, separated by a tiny distance in a vacuum, would experience a small but definite attractive force due to the differing quantum fluctuations of the electromagnetic field inside and outside the plates. His elegant formulation provided a precise mathematical description for this ethereal push. However, predicting such a subtle force is one thing. Actually measuring it is another entirely. The Casimir force is incredibly weak, typically in the order of piconewtons. To put that into perspective, a piconewton is 1/1,000,000th of a newton, or 12 newtons. The weight of a single red blood cell is roughly 10 piconewtons. Detecting such a minute force requires experimental setups of astounding precision, capable of isolating the plates from virtually all other influences. How do you measure something so tiny, when even the slightest vibration or stray electric charge could overwhelm the signal? Early experimental attempts in the 1950s, notably by M.J. Sparnay in 1958, provided qualitative evidence consistent with Casimir's prediction, but they lacked the quantitative accuracy needed for definitive proof. The challenges were immense: ensuring the plates were perfectly parallel, maintaining an ultra-high vacuum, shielding against electrostatic charges, which can easily be orders of magnitude stronger than the Casimir force, and isolating the apparatus from seismic vibrations and thermal fluctuations. It took decades for technology to catch up to the theoretical elegance of Casimir's idea. The definitive quantitative confirmation arrived nearly 50 years after Casimir's prediction. In 1997, a team led by Steve Lamoureux at Los Alamos National Laboratory achieved a groundbreaking experiment. Instead of two flat plates, which are notoriously difficult to keep perfectly parallel at nanometer scales, Lamoureux used a flat plate and a highly polished spherical lens. This geometry simplifies alignment and allows for a precise variation of the gap distance. His apparatus was a marvel of engineering, isolated in an ultra-high vacuum chamber, shielded from electromagnetic interference, and cooled to minimize thermal noise. The measurements were carried out with extraordinary care, ensuring that any residual electrostatic forces were meticulously identified and subtracted. Lamoureux's results were a triumph. The measured attractive force between the plate and the sphere matched Casimir's theoretical prediction to within a remarkable 5%. This was no longer just a theoretical curiosity. It was a tangible, experimentally verified reality. Since then, numerous other experiments have confirmed and refined these measurements, exploring different geometries and pushing the limits to even smaller distances, consistently validating the quantum nature of the vacuum. Doesn't this make you wonder what other hidden forces might be at play in the seemingly empty spaces around us? The scales at which the Casimir effect becomes significant are truly microscopic. We're talking about distances between plates ranging from a few tens of nanometers up to a few hundred nanometers. To grasp this, consider that the wavelength of visible light is typically between 400 and 700 nanometers. So these are gaps smaller than the wavelength of light itself. At these incredibly small separations, the Casimir force, though still tiny in absolute terms, can become a dominant interaction, even overwhelming gravitational or electrostatic forces if charges are meticulously controlled. It's important to clarify a common misconception. The Casimir effect does not violate the principle of energy conservation. Virtual particles, as their name suggests, are fleeting borrowers of energy, allowed by the Heisenberg uncertainty principle for incredibly short durations. The net energy of the vacuum, averaged over any meaningful period, remains zero. The Casimir effect arises from a different source in the distribution of this zero-point energy, not from a creation of energy out of nothing. It's a force, much like pressure, caused by an imbalance, not a source of extractable energy in the conventional sense. While the theoretical energy density of the vacuum is immense, enough to boil all Earth's oceans in a coffee cup of space, if it could be entirely harnessed, the Casimir effect demonstrates a force, not a straightforward way to tap into that energy. To separate the plates after they've been pulled together by the Casimir force would require expending energy. The implications of the Casimir effect extend far beyond just validating a physics theory. For one, it provides indisputable experimental evidence for the existence of virtual particles and the dynamic nature of the quantum vacuum, a cornerstone of quantum field theory. It confirms that empty space is a vibrant, energetic medium, reinforcing our understanding of the universe at its most fundamental level. On a practical level, the Casimir effect has become a critical consideration in the burgeoning field of microelectromechanical systems, MEMS, and nanoelectromechanical systems, NEMS. These are tiny devices, like microscopic gears, sensors, and actuators, often fabricated on silicon chips. As the components of these devices shrink to nanometer scales, the Casimir force, once negligible, can become significant. It can cause tiny parts to stick together, a phenomenon known as stiction, leading to device failure. Engineers designing these microscopic machines must now account for and even try to mitigate the Casimir effect. Conversely, some researchers are exploring ways to engineer the Casimir force, perhaps even to create repulsive Casimir forces by using specific materials or geometries to prevent stiction or even to enable novel nanoscale devices. Could this subtle force one day be harnessed for entirely new technologies? But perhaps the most profound significance of the Casimir effect lies in its connection to cosmology. If the quantum vacuum, on microscopic scales, can exert a real measurable force, what does this imply for the vast emptiness that permeates the entire cosmos? The Casimir effect offers a tangible, experimentally verified link between the bizarre world of quantum fluctuations and the macroscopic concept of vacuum energy. It shows that vacuum energy is not just a theoretical construct, but a physical reality capable of influencing matter. This realization naturally leads us to wonder, could this same vacuum energy, acting on the grandest possible scale, be responsible for some of the most mysterious forces shaping the universe itself? Could the emptiness that isn't empty be the hidden driver of cosmic destiny? We have explored the astonishing truth that even the deepest vacuum of space is not truly empty, but a vibrant, seething quantum foam. We've seen how this ceaseless activity, driven by the fleeting appearance and disappearance of virtual particles, can exert a measurable influence, as demonstrated by the delicate Casimir effect. But what if this microscopic dance of quantum energy ripples out, influencing not just tiny plates in a laboratory, but the very fabric and fate of the entire cosmos? Could the emptiness that isn't empty be shaping the universe on its grandest scales? This question takes us on a journey through some of the most profound intellectual shifts in the history of science, beginning in the early 20th century. Imagine the scientific landscape then. The universe was largely perceived as static, unchanging and eternal on its largest scales. While stars and galaxies moved, the overall structure of the cosmos was thought to remain fixed. This was the prevailing view when Albert Einstein unveiled his revolutionary theory of general relativity in 1915. This theory redefined gravity not as a force pulling objects together, but as a curvature in the fabric of space-time itself, caused by mass and energy. Planets orbit the Sun not because they are pulled by an invisible force, but because the Sun's immense mass warps the space-time around it, and the planets follow the shortest path through that curved geometry. When Einstein applied his new equations to the universe as a whole, he encountered an unexpected problem. His equations, in their simplest form, predicted a dynamic universe, one that should either be expanding or contracting. This contradicted the widely accepted idea of a static cosmos. To reconcile his theory with the prevailing wisdom, and perhaps his own philosophical inclinations, Einstein introduced an additional term into his equations. He called it the cosmological constant, often denoted by the Greek letter lambda, L. This constant represented a pervasive, repulsive force inherent to space itself, acting against gravity. It was essentially an anti-gravitational energy embedded in the vacuum, designed to perfectly balance the attractive force of matter and thus maintain a stable, static universe. It was a mathematical fudge factor, a subtle adjustment to ensure his beautiful theory didn't immediately imply a universe in flux. For over a decade, the cosmological constant quietly sat in Einstein's equations, providing a theoretical basis for a static universe. But scientific understanding rarely remained still. While Einstein was refining his theories, astronomers were peering deeper into the night sky with ever more powerful telescopes. The early 20th century marked a pivotal era for observational astronomy, a time when humanity was just beginning to grasp the true scale and nature of the universe beyond our Milky Way. The stage was set for Edwin Hubble, working at the Mount Wilson Observatory in California, home to the then largest telescope in the world, the 100-inch Hooker telescope. Hubble embarked on painstaking observations of distant nebulae, fuzzy patches of light that many astronomers believed were simply gas clouds within our own galaxy. Using a technique involving Cepheid variable stars, a special type of star whose intrinsic brightness is directly related to the period of its pulsations, Hubble could calculate their distances with remarkable accuracy. These Cepheid variables act like cosmic standard candles, allowing astronomers to gauge distances across vast cosmic gulfs. What Hubble discovered was nothing short of revolutionary. He found Cepheid variables in several of these nebulae, and their distances were immense, far exceeding the estimated size of the Milky Way. This definitively proved that these nebulae were not gas clouds, but entirely separate galaxies, each a sprawling island of billions of stars, much like our own. The universe, it turned out, was far vaster than anyone had imagined, teeming with countless galaxies, but Hubble's most profound discovery was yet to come. Building on earlier work by astronomer Vesto Slipher, who had observed that most distant galaxies appeared redshifted, meaning their light was stretched to longer, redder wavelengths, Hubble meticulously measured the distances and redshifts of dozens of galaxies. Redshift, in this cosmological context, is interpreted as a Doppler effect, just as the pitch of an ambulance siren drops as it moves away from you. The light from a galaxy shifts to redder wavelengths if that galaxy is moving away from us. In 1929, Hubble announced his groundbreaking finding, now famously known as Hubble's law. The farther away a galaxy is, the faster it appears to be receding from us. This wasn't merely a random motion, it was a systematic pattern. This observation led to an inescapable conclusion. The universe is not static, but expanding. Space itself is stretching, carrying galaxies along with it, much like dots drawn on the surface of an inflating balloon. The balloon's surface expands, and the dots move farther apart, even though they aren't moving across the surface in the traditional sense. This discovery sent shockwaves through the scientific community. It meant that the universe had a beginning, a point in time when it was much smaller and denser, a concept that would later evolve into the Big Bang theory. And what about Einstein's cosmological constant? His carefully placed term, designed to keep the universe static, was suddenly rendered unnecessary, even incorrect. Upon learning of Hubble's findings, Einstein famously called the introduction of the cosmological constant his biggest blunder. He felt he had missed the opportunity to predict the expanding universe from his own equations, an insight that could have been a crowning achievement of his theory. Yet, as with many blunders in science, the story of the cosmological constant didn't end there. In a fascinating twist of fate, this seemingly discarded concept would eventually resurface, not as a mistake, but as a central player in one of the greatest mysteries of modern cosmology. The universe was expanding, that much was clear, but the question of how it was expanding and why remained open. For decades, scientists largely assumed that gravity, the dominant force on cosmic scales, would cause the expansion to slow down over time. Just as a ball thrown upwards eventually slows due to Earth's gravity, the universe's expansion was expected to decelerate due to the mutual gravitational pull of all its matter. The cosmological constant, though, offered an alternative, a persistent, repulsive force. Imagine the vastness of space stretching between galaxies, seemingly empty. If the quantum foam we discussed earlier is truly a fundamental property of reality, if virtual particles are constantly popping in and out of existence everywhere, then even this seemingly empty space must possess an inherent energy. This is where the idea of vacuum energy takes on a cosmic significance. If every cubic centimeter of empty space contains a tiny, irreducible amount of energy, then as the universe expands and creates more empty space, the total amount of this vacuum energy would increase. Unlike matter or radiation, which become diluted as the universe expands, the energy density of the vacuum would remain constant. This is a crucial distinction. If space itself has an intrinsic energy, then as new space is created, new vacuum energy is also created within it. This constant energy density permeating all of space would exert a constant outward pressure, pushing the fabric of the universe apart. This is precisely what Einstein's cosmological constant described, a form of energy that doesn't dilute with expansion and acts as a repulsive force. Could it be that Einstein's biggest blunder was not a mistake at all, but a premature glimpse into a profound truth, a theoretical entity waiting for observational confirmation? The idea that the vacuum itself could possess energy that drives cosmic expansion is a compelling one, bridging the microscopic world of quantum mechanics with the macroscopic expanse of the cosmos. This concept lays the groundwork for understanding one of the most perplexing discoveries of the late 20th century, the accelerating expansion of the universe, a phenomenon attributed to a mysterious force now known as dark energy. The cosmological constant, once discarded, was poised for a spectacular comeback. For countless millennia, humanity gazed at the night sky, perceiving a universe of seemingly unchanging stars, a grand static tapestry. Then, in the early 20th century, a profound revelation reshaped our cosmic view. The universe is not static. It is expanding, with galaxies rushing away from one another. For decades, it was widely assumed that this expansion, like a ball thrown upwards, must be slowing down, gradually yielding to the relentless pull of its own gravity. Perhaps one day, it might even reverse into a big crunch. But then, something truly astonishing began to emerge from the cosmic darkness, something that challenged every prior assumption and unveiled a hidden driver of unimaginable power. Imagine peering deep into the cosmos, not just to see what is there, but to measure the very fabric of its expansion over billions of years. This monumental task required a cosmic ruler, a reliable beacon capable of shining brightly enough to be seen across vast intergalactic distances. Scientists found their answer in a specific type of stellar explosion, known as a Type I supernova. These aren't just any exploding stars. They are the dramatic finales of white dwarf stars in binary systems. A white dwarf, the dense remnant of a star like our Sun, can siphon matter from a companion star. As it accumulates more and more material, it eventually reaches a critical mass, about 1.4 times the mass of our Sun, known as the Chandrasekhar limit. At this precise point, the white dwarf becomes unstable and undergoes a thermonuclear runaway, detonating with a spectacular consistent luminosity. Because they all explode at roughly the same intrinsic brightness, Type Ia supernovae act as incredibly precise standard candles across the universe. By comparing their observed apparent brightness to their known intrinsic brightness, astronomers can accurately determine their distances, and by measuring the redshift of the light from their host galaxies, they can determine how fast the universe was expanding at the time the light left the supernova. In the late 1990s, two independent teams of astronomers embarked on a quest to measure the universe's expansion rate with unprecedented precision. The Supernova Cosmology Project, led by American astrophysicist Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, spearheaded by Brian Schmidt of the Australian National University and Adam Rees of Johns Hopkins University, meticulously scanned the skies for these distant Type Ia supernovae. Their goal was to see if the cosmic expansion was indeed slowing down as expected. As they gathered data from dozens of supernovae, some exploding billions of light-years away, a perplexing pattern began to emerge. The distant supernovae appeared fainter than they should have been if the universe's expansion was decelerating. Fainter meant they were further away, and if they were further away than predicted, it could only mean one thing: the universe had been expanding faster. In the past than current models suggested, in a stunning, almost simultaneous announcement in 1998, both teams published their findings, revealing that the expansion of the universe was not slowing down, but was in fact accelerating. This was a truly revolutionary discovery, earning Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It was as if you threw a ball into the air, and instead of slowing down and falling back, it suddenly started speeding up, defying gravity and soaring ever faster into the sky. What force could possibly be driving such a relentless, ever-increasing expansion against the pull of all the universe's matter? This mysterious force, this cosmic accelerant, was given a name that speaks to its elusive nature: dark energy. It is dark not because it absorbs light, but because it does not interact with light or any other form of electromagnetic radiation. We cannot see it, feel it, or directly detect it with our telescopes. Yet, its gravitational influence on the universe's expansion is undeniable. Dark energy is believed to be a form of pervasive energy inherent to space itself. Unlike matter or even dark matter, which become diluted as the universe expands, the energy density of dark energy is thought to remain constant. As space expands, more empty space is created, and with it, more dark energy comes into existence. This effectively creates an ever-increasing repulsive force, pushing galaxies further and further apart at an accelerating rate. To truly grasp the dominance of dark energy, consider the cosmic inventory. All the ordinary matter we can see and interact with, stars, planets, gas, dust, everything that makes up galaxies, including ourselves, accounts for only about 5% of the universe's total energy density. Another roughly 27% is attributed to dark matter, an invisible substance that interacts gravitationally but does not emit or absorb light. It acts as a kind of cosmic scaffolding, holding galaxies together. But the vast majority, approximately 68% of the universe's total energy density, is comprised of this enigmatic dark energy. This means that the universe is not primarily made of stars and galaxies, or even dark matter, but of this invisible, pervasive energy that dictates its ultimate fate. Doesn't it strike you as profoundly strange that the dominant component of our universe is something we still barely understand? The simplest and most widely accepted explanation for dark energy is that it is precisely what Albert Einstein called the cosmological constant, a constant energy density permeating all of space. And if this is true, then dark energy is essentially the macroscopic manifestation of the vacuum energy we explored earlier, the ceaseless quantum foam of virtual particles popping in and out of existence in even the emptiest regions of space. This brings us face to face with one of the most profound and unsettling discrepancies in all of modern science, the cosmological constant problem. Our most successful theory of the very small quantum field theory provides a way to calculate the expected energy density of the vacuum. If you sum up the zero-point energies of all known quantum fields, the minimum possible energy that a quantum system can possess, even in its lowest energy state, the theoretical prediction for vacuum energy is astronomically huge. Imagine taking all the fundamental particles and forces and calculating the energy associated with their quantum fluctuations in every cubic centimeter of space. The numbers are staggering. Even if we consider a conservative cutoff for these calculations, say, at the Planck scale, the smallest meaningful unit of length in quantum gravity, around 10-35 meters, the predicted vacuum energy density is still incredibly immense. To give you a sense of scale, theoretical calculations suggest that a mere coffee cup's worth of this quantum vacuum energy could contain enough energy to boil all the Earth's oceans, or even more. Some estimates put the theoretical vacuum energy density at a staggering 10^3 ergs per cubic centimeter, or roughly 1096 kilograms per cubic meter in energy equivalent mass. Now, let's compare this theoretical behemoth to the observed reality. The dark energy density, as inferred from cosmological observations, from the accelerating expansion of the universe, from the precise patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, and from the distribution of galaxies across vast scales, is incredibly tiny. It is measured to be approximately 10^9 joules per cubic meter. This means the observed value of dark energy is about 10^27 kilograms per cubic meter in energy equivalent mass. The difference between the theoretically predicted vacuum energy and the cosmologically observed dark energy is an astounding factor of 10^20. This is not a small error, not a slight miscalculation. It is a discrepancy so vast, so monumental, that it represents the largest mismatch between theory and observation in the entire history of science. Imagine predicting the weight of an apple, and your calculation is off by a factor that would encompass the entire mass of the observable universe, and then some. This monumental discrepancy, a factor of 120 zeros, is more than just a puzzle. It is a profound chasm in our understanding, a glaring signal that either our quantum field theories are fundamentally incomplete, or our understanding of gravity on cosmic scales is flawed, or perhaps both. So how can we reconcile these two vastly different views of reality? The universe seems to be fine-tuned to have an incredibly small, but non-zero, vacuum energy. If the vacuum energy were much larger and positive, the universe would have expanded so rapidly in its infancy that galaxies, stars, and ultimately life would never have had the chance to form. If it was slightly negative, the universe might have collapsed back on itself long ago. The fact that we exist to observe this small, positive dark energy leads some scientists to ponder the anthropic principle, suggesting that we simply live in a universe where the conditions allow for our existence. However, most physicists consider this an unsatisfying explanation, seeking a deeper, more fundamental physical reason. The cosmological constant problem highlights a deep tension between our two most successful theories of physics: quantum mechanics, which describes the universe at its smallest scales, and general relativity, which describes gravity and the universe at its largest scales. Reconciling them into a unified theory of quantum gravity is one of the holy grails of modern physics, and the resolution of the dark energy puzzle is likely intertwined with this grand challenge. Perhaps there are other quantum fields that contribute negative energy, almost perfectly cancelling out the vast positive vacuum energy, leaving behind only the minuscule residue we observe. But why would this cancellation be so exquisitely precise? This concept of fine-tuning presents its own set of challenges. The long-term implications of dark energy are profound. If it truly is a constant energy density of space, then the universe's accelerated expansion will continue indefinitely. Galaxies will continue to recede from one another at ever-increasing speeds. Over unimaginable timescales, the space between galaxy clusters will stretch so dramatically that eventually, even the light from the most distant galaxies will never reach us. Our observable universe will shrink, becoming an increasingly isolated island in an ever-expanding, increasingly empty void. The universe's ultimate fate, a big freeze or heat death, seems to be sealed by this hidden driver, pushing everything apart until only isolated cold remnants remain. The emptiness that isn't empty, the quantum foam, might not just be a microscopic curiosity. It might be the silent orchestrator of the universe's grand, accelerating destiny. The journey through the seemingly empty expanse of space has led us to a profound realization. The void is anything but. From the incessant quantum foam bubbling at the smallest scales, to the mysterious dark energy accelerating the universe's grandest expansion, emptiness has revealed itself as a vibrant, energetic entity. Yet, despite the compelling evidence from experiments like the Casimir effect and observations of distant supernovae, the exact nature of this vacuum energy, particularly its cosmic manifestation as dark energy, remains one of the most significant unsolved puzzles in modern physics. What hidden truths does this energetic void still hold? And how might we finally unlock its secrets? The quest to understand this pervasive, invisible force is not static. It is a dynamic, global effort, stretching from earthbound observatories to sophisticated space telescopes orbiting above our planet's atmospheric veil. Scientists worldwide are designing and launching ambitious missions, each meticulously crafted to gather more precise data, hoping to catch a glimpse of dark energy's true character. These endeavors represent humanity's collective determination to decipher the universe's most elusive component, a component that dictates the very fate of all existence. Among these cutting-edge missions, the European Space Agency's Euclid Space Telescope stands as a prime example of our current scientific ambition. Launched in July 2023, Euclid is on a 6-year mission to map the large-scale structure of the universe across an immense span of space and time. Imagine a cosmic cartographer meticulously charting the positions and shapes of billions of galaxies over the past 10 billion years of cosmic history. Euclid achieves this by employing 2 primary instruments: a visible light imager and a near-infrared spectrometer and photometer. The visible instrument captures extremely sharp images of galaxies, allowing scientists to measure their shapes with unprecedented accuracy. This is crucial for a technique called weak gravitational lensing, where the gravity of massive structures in the foreground subtly distorts the light from background galaxies, making them appear stretched or smeared. By analyzing these subtle distortions, scientists can map the distribution of dark matter and, indirectly, dark energy throughout the cosmos. Simultaneously, Euclid's near-infrared spectrometer measures the redshift of galaxies. Redshift is the stretching of light waves as galaxies move away from us due to the universe's expansion, and it acts as a cosmic odometer, indicating how far away a galaxy is and how fast it is receding. By combining these distance measurements with the spatial distribution of galaxies, Euclid will create a 3-dimensional map of the universe. This map will reveal the intricate cosmic web, the vast network of galaxy clusters, filaments and voids, and how it has evolved over time. Any subtle changes in the rate of this evolution or the growth of these structures can provide vital clues about the properties of dark energy. Does its strength change over time? Is it truly a constant, as Einstein's cosmological constant suggests, or is it a dynamic field, perhaps slowly decaying or strengthening? Euclid's data aims to distinguish between these possibilities, pushing the boundaries of our understanding. Complementing Euclid's observations is NASA's Nancy Grace Roman Space Telescope, formerly known as W-FIRST, set for launch in the mid-2020s. Roman is designed with an equally ambitious goal: to explore the mysteries of dark energy, exoplanets, and infrared astrophysics. Its primary instrument is a wide-field instrument, equipped with a mirror of the same size as the Hubble Space Telescopes, but offering a field of view 100 times larger. Imagine taking a photograph of the night sky, and instead of seeing a tiny postage stamp of galaxies, you capture an entire panoramic vista in a single shot. This vast field of view allows Roman to survey enormous swathes of the cosmos with remarkable speed and efficiency, collecting data that would take other telescopes decades to acquire. Roman will employ several independent methods to probe dark energy. One key technique involves using type Ia supernovae, the very standard candles that revealed cosmic acceleration in the first place. By observing thousands of these exploding stars across billions of light years, Roman will be able to measure their distances with unprecedented precision, refining our understanding of how the universe's expansion rate has changed over cosmic history. Another method is baryonic acoustic oscillations, BAO. These are relic sound waves from the early universe that imprinted a characteristic scale onto the distribution of matter. Imagine ripples on a pond that have been frozen in time, now visible in the clustering of galaxies. By meticulously measuring this cosmic ruler at different epochs, Roman can precisely track the universe's expansion history, providing another independent check on dark energy's behavior. The sheer volume and quality of data from both Euclid and Roman are expected to significantly tighten the constraints on dark energy models, potentially ruling out some theories and strengthening others. While these observational behemoths gather data, the theoretical arena remains a vibrant battleground of ideas. The greatest challenge, the cosmological constant problem, continues to loom large. As discussed earlier, quantum field theory predicts a vacuum energy density that is an astounding 120 times greater than the observed dark energy density. To put this into perspective, imagine the weight of a single atom compared to the weight of all the stars in the observable universe combined. The discrepancy is even more extreme. This vast chasm between prediction and observation represents a fundamental breakdown in our understanding, a profound tension between the two pillars of modern physics: quantum mechanics, which describes the very small, and general relativity, which describes gravity and the very large. Scientists are actively exploring various theoretical avenues to bridge this gap. One prominent alternative to Einstein's simple cosmological constant is the concept of quintessence. Imagine dark energy not as a fixed, unchanging property of space, but as a dynamic, evolving field similar to other fundamental fields like the electromagnetic field. This quintessence field would have its own energy, which could vary over time and space, potentially explaining why dark energy's influence became dominant only relatively recently in cosmic history. Such a field might cause the universe's expansion to accelerate at a rate that is not perfectly constant, offering a distinct observational signature that missions like Euclid and Roman are designed to detect. If the expansion rate shows subtle variations, it could point towards a dynamic quintessence rather than a static cosmological constant. Another class of theories involves modified gravity. Instead of introducing a new component like dark energy, these theories propose that Einstein's theory of general relativity itself might need modification on cosmic scales. Perhaps gravity behaves slightly differently over vast distances, or at extremely low accelerations, leading to an apparent acceleration without the need for a mysterious energy component. For example, some models propose modifications to the geometry of spacetime or the fundamental laws of gravity, leading to effects that mimic dark energy. Distinguishing between dark energy and modified gravity is incredibly challenging, requiring extremely precise measurements of how galaxies cluster, how light bends around massive objects, and how the expansion rate evolves. The data from the new generation of telescopes will be crucial in testing these subtle differences, pushing the boundaries of our understanding of gravity itself. Ultimately, the resolution of the dark energy mystery and the cosmological constant problem might require nothing less than a unified theory of everything, a framework that seamlessly integrates quantum mechanics with general relativity. Such a theory, often sought in concepts like string theory or loop quantum gravity, aims to describe all fundamental forces and particles within a single coherent mathematical structure. It is hoped that within such a grand theory, the nature of vacuum energy would emerge naturally, perhaps with a mechanism that explains why its observed cosmological value is so incredibly small compared to theoretical predictions. This ambition represents the pinnacle of theoretical physics, promising not just an answer to dark energy, but a complete picture of reality at its most fundamental level. Beyond the grand theoretical implications, understanding vacuum energy and dark energy also has subtle yet profound practical significance for humanity. While quantum foam and dark energy do not directly power our homes or solve immediate global challenges, Their study fosters critical advancements in technology and scientific methodology. The sophisticated instruments developed for missions like Euclid and Roman push the boundaries of sensor technology, optics, and data processing. These innovations often find their way into other fields, from medical imaging to satellite communication. Moreover, the very act of grappling with such deep cosmic mysteries compels us to refine our understanding of fundamental physics, which has historically led to unforeseen technological revolutions. Consider the abstract theories of electromagnetism that eventually gave us electricity, radio, and the internet. Who can say what practical breakthroughs might emerge from a complete understanding of the quantum vacuum? Perhaps the most enduring significance lies in the cultural and scientific impact. The exploration of vacuum energy and dark energy expands our cosmic perspective, reminding us that reality is far stranger and more complex than our everyday experiences suggest. It challenges our intuitive notions of emptiness and matter, forcing us to confront the limits of our current knowledge. This journey of discovery fuels human curiosity, inspiring new generations of scientists, engineers, and thinkers. It encourages a deeper appreciation for the intricate beauty and profound mysteries woven into the fabric of the universe, fostering a sense of wonder that transcends disciplinary boundaries. Let us reflect for a moment on the incredible journey we have undertaken. We began by questioning the very notion of emptiness, discovering that at the quantum level, space seethes with virtual particles, a ceaseless quantum foam. We saw how this theoretical concept gained experimental validation through the subtle yet undeniable Casimir effect, where the vacuum itself exerted a measurable force. Then, our gaze lifted to the cosmic scale, where Albert Einstein's initial blunder of the cosmological constant was resurrected as a potential explanation for the universe's accelerating expansion, a phenomenon dramatically confirmed by the observations of Edwin Hubble and the supernova teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees. This led us to the enigmatic dark energy, the dominant component of our universe, driving galaxies apart at ever-increasing speeds. The paradox endures. How can a space that is fundamentally empty, a vacuum, possess such immense energy that it dictates the ultimate fate of the cosmos? This question, born from the tiny jitters of quantum foam, now guides the most ambitious space missions and inspires the deepest theoretical investigations. The future promises a deluge of data from telescopes like Euclid and Roman, allowing us to scrutinize dark energy's behavior with unprecedented precision. Will it turn out to be Einstein's simple cosmological constant, a fixed property of space? Or will it be a dynamic quintessence field, evolving with the universe? Could it even be a sign that our understanding of gravity itself is incomplete on cosmic scales? The universe, in its boundless expanse, continues to reveal layers of complexity and wonder that challenge our most fundamental assumptions. The emptiness that isn't empty serves as a powerful reminder that our scientific journey is far from over. Each answer we uncover invariably leads to new, more profound questions. As we continue to peer into the cosmic void, listening to the quiet roar of quantum fluctuations and charting the accelerating dance of galaxies, we are not just seeking knowledge. We are engaging with the very essence of existence, forever humbled and enthralled by the beautiful, strange, and endlessly mysterious universe we call home. The true nature of this emptiness and the energy it contains remains the ultimate frontier, beckoning us to look ever deeper, to question ever more profoundly, and to marvel at the cosmic tapestry that unfolds before us.